Part 284C3M1b7c8e13c9c6d3p38d19d7b9d14b. This is line 22f1fa19c3m1b7c8e13c9c6d3p38d19d7b9d14b. Wigner functions 2 signals 5G Wow Seti. There's the alien radio signal. So this is the Wigner quasi-probability distribution, part 2, for vacuum light signals for the WOW data long distance communication signal ideas. Here's March 23rd, 2013. The keyword ideas are radiative energy, bilinear form, and Fermi line, Fermi Edge Singularity. That's with Mesoscopic X-Ray Edge Problem and Mesoscopic fluctuations. It's from this line of data, cavity 3 Optomechanics, and then it went to Wigner functions 1 signals. So the keyword mesoscopic fluctuations plus quantum optics, added to non-classical light, then Glauber Sudarshan P representation, non-classical light, cavity optomechanics, cavity optomechanics, and Wigner functions. So the Wigner functions and Wigner quasi-probability distribution part 2, the Wigner function in relation to other interpretations of quantum mechanics. This is a quote probably from Wiki. I seem to have forgot to put that down. It has been shown that the Wigner quasi-probability distribution function can be regarded as H, deformation of another phase space distribution function that describes an ensemble of de Broglie-Bohm causal trajectories. Basil Hiley has shown that the quasi-probability distribution may be understood as a density matrix re-expressed in terms of a mean position and momentum of a cell in phase space, and de Broglie-Bohm interpretation allows one to describe the dynamics of the centers of such cells. There is a close connection between the description of quantum states in terms of the Wigner function and a method of quantum states reconstruction in terms of mutually unbiased bases. Keyword: uses of the Wigner function outside quantum mechanics. Figure 7. A contour plot of the Wigner-Ville distribution for a tripped pulse of light. The plot makes it obvious that the frequency is a linear function of time. In the modeling of optical systems such as telescopes or fiber communication services, the Wigner function is used to bridge the gap between simple ray tracing and the full wave analysis of the system. Here the pH is replaced with K equals K, sin O equals K, and some other symbol there, in the small angle paraxial approximation. In this context, the Wigner function is the closest one can get to describing the systems in terms of arrays at position X and angle, while still including the effects of interference. If it becomes negative at any point, then simple ray tracing will not suffice to model the system. In signal analysis, a time-varying electrical signal, mechanical vibration, or sound wave are represented by a Wigner function. Here X is replaced with the time and pH is replaced with the angular frequency W equals 2 pi f, where f is the regular frequency. In ultrafast optics, short laser pulses are characterized with the Wigner function using the same f and t substitutions as above. Pulse defects such as chirp, the change in frequency with time, can be visualized with the Wigner function. In quantum optics, x and p divided by h are replaced with the x and p quadratures, and the real and imaginary components of the electric field see coherent state. The plots in figure 1 are of quantum states of light. The keyword is Wigner functions, Wigner quasi-probability distribution part 3, measurements of the Wigner function, will be in the next video. Thanks for watching.